Now we come to the last part of molecular assembly. So after we know all about the molecular assembly in biological system, now we are going to look outside our body to see the molecular assembly in artificial system or synthetic system, I would say. So normally the molecular assembly have to be very selective. And the molecular assembly can be divided, the selectivity of the assembled can be divided into two types, the ion recognition and the molecular recognition. So the recognition meaning that the host molecules can recognize a specific gassed ions or molecular to be trapped into it. And the specific binding over here normally resulted from shape of the molecules and size of the molecules, for example. Now I'm going to give you some examples of these molecular recognition and how they're going to constructing a very huge system of molecules. First of all, this is an example of ion receptor. So this work, they're trying to catch kind of potassium ion. What they use as a receptor is these macrocyclic molecules. It's not a very huge molecule actually, but it's composed of 1, 2, 3, 4, 5, 6 oxygen atoms labeled in red color. And linked between these are the two units of the thiophene. So the potassium ion, which is positive charge, can have interactions with the negative pockets of oxygen-rich ring over here. So as a result, we have kind of binding between potassium ion and the crown ether ring. Right? So this is called recognition. This ring cannot complex with a very huge atoms like cesium or rubidium because of the size, right? So we have a relatively small pocket which is suitable for the potassium ion. Bigger ion like cesium is not suitable for this, or very small ion like lithium ion is also not very suitable for this one. So we have a selectivity. Right? So this is called ion recognition because the molecules can recognize that we have to catch up the potassium ion only, not any other thing else. Right? So we have selective binding here. But if the selectivity is very strong, we may call it as specific binding instead of selective binding. So this is ion recognition. Another example here is the molecular receptor. Right? So we have molecular recognition. So very similar to the first one, but in the crown ether ring here, we insert kind of benzene ring inside. Okay? So this benzene ring is an electron-rich benzene ring because it's connected to two of the oxygen atoms nearby. So by resonance effect, the electron pair on your oxygen atom can then resonance into the aromatic ring in here. So we have electron rich of the benzene ring over here, and also electron rich of the thiophene unit by dithiophene unit over here. So this molecule can have high affinity binding with the paraquat. This is the paraquat molecules. So composed of two benzene ring together, and we have the blue color over here and nitrogen ion, but it is positively charged. So we have two of the N+, right, which make this molecule electron poor. So these can have kind of charge transfer complex. We have two of the electron-rich benzene ring and thiophene ring, and the electron poor of the paraquat. So we can have charge transfer complex over here. So we have a specific binding or selective binding with the paraquat, which is the together with the pi-pi stacking as well, right? So the shape of the molecules have to be kind of benzene-like structure, and also the electron density have to be very low in order to have a nice um, electron transfer. What to say? The charge transfer complex. I'm sorry. So by the designing of the gas molecules, we can trap selectively the by designing the host molecules, we can have very high selectivity for gas recognition like this. Okay, this is very simple, but we can make something in bigger scale. For example, the metallopolymer over here. So the molecules you see over here composed of many nitrogen atoms, right? So the nitrogen atoms here can have a electron pair. As you can see, the electron pair of this nitrogen, and this nitrogen are in sp2 hybrid orbitals and pointing toward this area. So three of the nitrogen atoms over here forming a kind of negative pocket, which is suitable to complex with a transition metal ion, for example. So this is a host molecule, and because we have two sides, right hand side and the left hand side, so both sides can complex with the metal ion. So I'm gonna symbolize the molecule over here by this kind of structure. So with a divalent metal ion, we can then construct a polymeric structure of this kind of system, which is called metallopolymer. So the metallopolymer is a kind of linear structure composed of these molecules and the divalent transition metal, right? We have the complex like this. But if we move further from divalent transition metal to be trivalent transition metal, so what we can see is a trivalent transition metal can complex with three of the ligands. So what we can have here at the very end is this two-dimensional structure, right, or the network of the polymer. Or we may say that we have a cross-linked polymer, cross-linked metallopolymer out of this kind of ligand. So we have metal organic framework, right, MOF, metal organic framework, because starting from metal ion and the organic molecules, constructing kind of network covalent, network polymer, thing like that. So the network polymer can expand it from 2-dimension to be 3-dimension, as showing you here in this structure, in this slide. So first of all, the greenish color over here is the kind of dichromate ion, and the orange color here is a kind of similar to paraquat, but we insert a benzene ring in the center, and we also have the nickel. So nickel, which is 2+, right, we can have the ionic interaction with the dichromate ion, and also with the electron pair on nitrogen atom to both sides of the nitrogen atoms in the central molecules over here. So apparently at the end we have the structure on the right hand, kind of 3-dimensional network, that we have the balls of nickel, okay, depicted as a ball, which have kind of complexation with the rods of green color and the rod of the orange color. So at the end we have 3-dimensional structure, densely packed, systematic, and well organized. And we can make use of this kind of thing as well. So for example, this kind of molecular structure can be used as a gas absorber. So as you can see here, on the right hand side is absolute pressure, on on the x-axis, on the z-axis is the quantity absorbed. So we have two gas molecules or gases, the acetylene and the carbon dioxide. So both acetylene and carbon dioxide can be absorbed here into a tiny little gaps between the structures, because we have kind of grid-like structure from the self-assembled network of nickel dichromate and the ligand. Right? So we can construct a three-dimensional network by like complexation between the ligands and the metal ion. Okay, that's the ion recognition, making a huge structure of the three-dimensional grid. Now, not only the metal complex, right, but organic complexation can also constructing two-dimension, three-dimension framework as well. So this is a inclusion complex network. So what you can see here, we have two components. On the right hand, a donut-shaped structure is called cucubituril. Cucubituril composed of this kind of structure. Actually, it is starting to synthesize this molecule from the urea. Okay, as you can see, we have two of the urea unit, and then condense the urea unit with the kind of oxaldehyde. So they condense the oxaldehyde together with the urea. Actually, these two ends are hydrogen atoms, not the carbon. And after you have this dimer, you condense again with the formaldehyde. So this is the first formaldehyde and this is the second formaldehyde. So both end, top and bottom end. And then they cyclize themselves together into kind of repetitive unit. Cucubituril 8 means that you have 8 subunits of this monomer, right? And then they form kind of donut-shaped structure. So this is cucubituril 8. And the cucubituril 8, because we have non-polar parts in the center, they can trap the non-polar molecules, and we call this as inclusion complex. So we have this structure on the left hand. Oops, sorry. So the left hand structure composed of the core structure, which is labeled in the blue, in the white color, and we have the yellow color, positive charge, and we also have the blue color, which is photoactive unit. This is diazobenzene. Diazobenzene, you have two kind of geometrical isomer. This is trans isomer. They can switch to be cis isomer using one particular wavelength and then switch back to the trans isomer with another wavelength. Okay, these are the properties of the thing composed in the system. So how we can make use of it? Okay, as you can see from the picture over here, that there are two states. Okay. We have monomer states, and then they can complex using inclusion complex with the cucubituril 8 to have this blue color. So the blue color part, the blue color side is the inclusion complex of these molecules and cucubituril. Okay, so they can link the cucubituril complex with two molecules of trans 1. Trans 1 is the name of this compound. So cucubituril complex with two molecules of trans 1. So part of the molecules get into the hole of the donut, okay, and from two molecules. So as you can see, cucubituril number 8 is very huge. So they can host two of the arms, right? So first arms from the first molecule and second arms from the second molecules, they have inclusion complex. So after you have inclusion complex, you have this kind of network. So this is two-dimension network. right? So this two-dimensional network can act as a molecular sieve, which is a very small pore size. But this can switch to be monomer again using 365 nanometer laser or lights. Okay. Then the complex cleaves to be the red side on the right hand. And if you switch it back with 420 nanometer, it turns back to be blue states here on the left hand. And then the porosity of the two-dimensional sheet can be reconstructed. Okay. The question is, what happened in this system? Why 365 can destroy the network, and why 420 can reconstruct the network? So first of all, you have to identify the complexation. I want you to think about two units of the trans one, complex together in the whole of the cucubitriol first, and then think about the photoresponsive at two different wavelengths later, right? So you have to identify the blue part, the blue side first, how the complexation can happen, and then you can think about why the photon can cleave out the complexation. Okay, so this is the assignment. Thank you very much for your attention. And thank you very much indeed. And this is the end of my talk about the molecular assembly.